Anyway, for this tutorial, I forgot to ask, how was your week? How's everyone's week? Hey, Taryn, I heard that a lot of you have multiple term tests. True? Two yesterday. Wow. One tomorrow. Is that 236 for the one tomorrow? Yeah. Oh. Seems like a lot of you are my students for both courses. Am I your TA for 236? Yeah. Yeah, because my last tutorial, students were talking about 236 tests tomorrow as well. Well, hopefully it's not too bad. Let me see if she made the test already. Actually, not sure. So she told me that she just want you to test you the basic stuff. Uh, and let's see if it's actually basic stuff, right? Oh, she hasn't made the test yet. Yeah, so I can't tell you if it's actually basic stuff. She only typed one word for the first question. So, I don't know. Anyway, well, you don't have any tests for this course, so hopefully that's good news for you. You only have assignment and quizzes, although you have a lot of assignments and quizzes. It's kind of a lot of work still. Anyway, today's tutorial we will talk about reduction of order, and then I will talk about some theories of second order linear homogeneous equation. So those theorems are the same for higher order. So for nth order, you just need to generalize it to nth order. It's basically the same thing, except you have more solutions and more, more variables. And lastly, I will talk about homogeneous linear ODEs with constant coefficients. So we'll talk about characteristic equation. We'll talk about three different cases where you have distinct real roots, repeated roots, and complex roots. And that's the plan for today. Hopefully we can finish everything. I have finished everything from my last tutorial, so it should be fine. So the first one, reduction of order. This is for second order ODE. When you have this ODE and you are given a solution, remember for when you want to do this, you are given a solution. Okay, so you're given a solution y1, you don't know what your y2 is, so you suppose that your y2 equals to an unknown function vx multiplied by y1x, and then you take the derivative and second derivative, plug those two back into the ODE, and you should get this, which you can cancel out some terms, and eventually you should get you should be able to solve your v. Okay, and that can be simplified to be a first order ODE if you let v prime prime equals to u prime. So that's gonna be y1 u prime plus something, and then u equals to 0. So you can solve this first order ODE easily, and after you find your v, you can plug back into your y2 to find your y2. So I heard that you did this in lecture already, so I'll give you some time to work on the first example. And once you're done, I'll take it up. If you want, you can type or write on the screen as well. Feel free to do any whatever you need. Anyone finish the question already? Okay, so basically, as I mentioned before, what we're doing is we let y2 equals to an unknown function v times y1, and you compute y2 prime and y2 prime prime, plug those two back into the ODE. So let's plug it back into the ODE. Or vx squared equals to 0. Okay, and then let's open the bracket. That's gonna give you x to the 4 v prime prime plus 4x cubed v prime plus x 2x squared v minus 3x cubed v prime minus 6x squared v plus 4vx squared equals to 0. And you can tell that we have 2x squared v minus 6x squared v and plus 4x squared v. So those three terms cancel out, and those two terms can be combined together. So that's gonna be x to the 4 v prime prime plus x to the 3 v prime equals to 0. Alright, and since your x it's greater than 0, that means it's not 0. That means we can divide by x to the 4. So we can have v prime prime plus 1 over x v prime equals to 0. Now you can let u equals to v prime. So if you let u equals to v prime, then v prime prime is going to be u prime. So this whole ODE becomes u prime plus 1 over x u equals to 0. Okay, so now you can solve for this since it's like first order homogeneous linear equation. So this is, use integrating factor e to the 1 over x dx equals to e to the absolute value of x. Since x is greater than 0, that's the same as x. So we know that x u prime equals to 0. Then your xu equals to c, so u equals to c over x. and that's your v prime. So you know what your v prime is, so v is gonna be 1 over x, so ln x c ln x plus d, and your y2 is gonna be v times y1, so c ln x plus d times x squared, and your general solution is c1 x squared plus c2 I don't need c2 anymore since I have a few constants already. C ln x plus d x squared. So that's your final general solution. Any question? Where your c1, c, and d are constant. Question? Are we good? Okay, cool. So move on to other theorems of second order linear homogeneous equation. So as I mentioned before, the second order linear homogeneous equations, those theorems, and higher order, like nth order, they're basically the same thing. So I'm just doing second order for now. Existence and uniqueness. If p, q are continuous on the interval containing x0, which we talked about this before actually, then the solution of the initial value problem exists and I and it's unique. So we talked about this in last tutorial where I used a stronger theorem. I said if, so go back to this. Where did I mention this? Remember I used a stronger one, not this one. So probably here. Okay, I don't know where I mentioned it. Did I mention this? D, E. Oh, here. Oh, that's, never mind. That's, I mentioned for separable. So it's different. So existence and uniqueness of IVP. It's very similar for nth order as well. So nth order, you'll not just have P and Q, so you might have P1x, P2x, P3x, and so on. If they're all continuous, then the solution of the initial value problem exists and it's unique. So for example, this one. The next theorem, which is principle of superposition, is more important. I'm gonna put a star here, which means it's really important. This is saying that if y1x, y2x are solutions to the homogeneous, so let me highlight this part, has to be homogeneous linear second order. So it works for nth order as well, but it's just not just a second order anymore. It's nth order, homogeneous, linear. So those two terms are really important, homogeneous and linear. Okay, on the interval I, then y equals to c1x, c1y1 plus c2y2 is also a solution, where c1, c2 are arbitrary constant. So this means that if y1 and y2 are solutions to a homogeneous linear nth order ODE, then their linear combination is also a solution. That's all it means. Now I want you to verify those two solutions are solutions of the ODE, and then I want you to show that this is not a solution and explain why this does not contradict the principle of superposition. So give you some time to work on this. If you want, you can type or write on the typically give you interval. If it's not giving you such interval, they assume that it's an all real number. So for this course, most likely they are doing all the real numbers. Yeah. When I took 244, I took at St. George. Usually they give you a certain interval, but from what I see at UTN, most likely they give you real number. That's why it's not given, because it's real number. I will start writing because checking if their solutions are pretty simple, and I'm pretty sure everyone can do it already. So I checked if y1 and y2 are solutions, and indeed they are solution. Now I want to show that the linear combination of those two is not a solution in general. So let's check. Y equals to c1 plus c2 t to the 1 over 2. The y prime equals to 1 over 2 c2 t to the negative 1 over 2. Y prime prime equals to negative 1 over 4 c2 t to the negative 3 over 2. Now, left hand side equals to c1 plus C2 t to the 1 over 2 times negative 1 over 4 C2 t to the negative 3 over 4 over 2 plus 1 over 2 C2 t to the negative 1 over 2 squared. So this will give you a negative 1 over 4 C1 C2 t to the negative 3 over 2 minus 1 over 4 C2 squared t to the negative 1 plus 1 over 4 C2 squared t to the negative 1. So those two cancels out. You get negative 1 over 4 C1 C2 t to the negative 3 over 2. And you can tell that this does not equal to 0 unless t1 or t2 equals to 0. Okay, so generally speaking, this does not equal to 0. So why does it not contradict with principle of superposition? Anyone know? Well, from this, they are saying that the linear combination should also be a solution, but why do we not get a solution? Okay, if we go back, I highlighted the key point. It has to be homogeneous. So this is homogeneous. And also it has to be linear. You can tell that this is definitely not linear, okay? So this does not contradict with this because the ODE itself is not linear. Any question? Are we good? Linear part, okay. So this is saying that principle of superposition only apply to homogeneous linear ODE. But this is not linear. For linear, first of all, for each of the y term or y derivative terms, they have to be themselves. So either has to be y times or x, like independent variable, or you don't have y in that term. But here it's y multiplied by its derivatives. So that means it's not linear. That's first reason it's not linear. Second term, it has a square. Okay, has to be first order. For each of the y and its derivative, it has to be first order. If it's not first order, for example, here it's second order, or even if you have square root of y, that's not first order either, then it's not linear either. Does that make sense? Okay, cool. So let's move on. Wronskian. This is defined by the determinant of this matrix where the entry is y1, y2, and y1 prime, y1, 2. So if you have higher order, for example, you have, let's say, third order, then your Wronskian is y1, y2, y3, and this equals to the determinant of y1, y2, y3, y1 prime, y2 prime, y3 prime, and then y1 prime prime, y2 prime prime, and y3 prime prime. So it goes on like this. If you have 4 terms, then it's like y4, and then y1 prime prime prime, y2 prime prime prime, and so on. So if it's third order, then it should be 3 by 3. If it's fourth order, then it's 4 by 4, and so on. And we have 2 theorems. Oh, by the way, I forgot to mention, if your Wronskian is non-zero, then we call the solutions are linearly independent. Then the solutions are linearly independent. Then the solutions are linearly independent. So if they ask you if the solutions are linearly independent, then you need to check if the Womskian equals to 0. Does that make sense? And keep going. Okay, so suppose y1 and y2 are solutions to this ODE, then there is a choice of constants y1 and y2 for which this satisfies the VP if and only if this is non-zero. So it's, again, we're talking about non-zero Womskian. If this is non-zero, then you have C1, C2 satisfy the MVP. Okay? And also, if there is a point x0 where this is non-zero, then y equals to C1, y1 plus C2, y2 includes every solution of this. So if this is non-zero, then this is a family of solutions that includes every single solution of the ODE. Anyway, and we call those fundamental set of solutions. Yeah, that's just a definition. So if this is non-zero, then we call this is a fundamental set of solutions, your y1 and y2. So now I want you to show that y1 and y2 form a fundamental set of solution of this. Before you start, I want to emphasize something because last semester when I graded assignment, a lot of people lost mark for this. Whenever they ask you to show this is a fundamental set of solution, you need to first check if they are solutions first. So your first step is check if they're solution. Because they need to be solution first in order to be fundamental set of solutions. Okay, they didn't ask you to check because it's like hidden behind it. And then after you check that there are solutions already, and then you check if the Womskian is now 0. Okay, very important. If you only did one of those, then you don't get 4 marks. Again, I'll give you some time to work on this, and after you're done, I'll take it up. Okay, I'm gonna take it up because we still have a lot of materials to cover. So first of all, I need to check if they are solutions. y1 prime equals to 1 over 2 t to the power of negative 1 over 2. y1 prime prime equals to negative 1 over 4 t to the negative 3 over 2. And your left hand side equals to 2t squared negative 1 over 4t to the negative 3 over 2 plus 3t times 1 over 2t to the negative 1 over 2 minus t to the 1 over 2. So this equals to t to the 1 minus 2 times negative 1 over 2 plus 3 over 2 plus 1. And that's going to give you 0. And that equals to your right hand side. That means my y1 is a solution. y2 prime equals to t to the negative 1. y2 prime prime equals to negative t to the negative 2. So left hand side, wait, what am I doing? Negative t to the negative 2. And this is t 2t to the negative 3. Yeah, and left hand side equals to 2t squared 2t to the negative 3 plus 3t negative t to the negative 2 minus y is t to the negative 1. So that equals to t to the negative 1 times 4 minus 3 minus 1, which equals to 0. And that's right hand side. So we check those two are indeed solutions of the ODE. Now we need to check if the Wurmskian is 0. So Wurmskian equals to the determinant of y1, y2, and the y1 prime, y2 prime, okay, which equals to negative 3 over 2 t to the negative 3 over 2. So this is definitely not 0 because our t is greater than 0. T is greater than 0 means it can never be 0, so this cannot be 0. That means the whole term can never be 0. So that means, therefore, my y1 and y2 are indeed fundamental. Okay, form, let's say y1 and y2 form a fundamental set of solutions. And you can also write the general solutions down. Anyway, let me write it down. C1 t to the 1 over 2, and then plus C2 t to the negative 1 for t greater than 0. Any question? So basically, if they ask you to check if they're a fundamental set of solutions, you can check if they're solutions and then check if the Wurmskian is 0. Yes, if they are linearly independent. Because right here, the solution with this not equal to 0 is called the fundamental set of a solution. But just let me see what your homework is asking. they ask you verify if they're linearly independent, right? Let me see. Verify our solutions to ODE and if their wall scan is non-zero. Yeah, yeah. So we just need to plug them back in and then compute their wall scan. Anyway, back to here. Does this make sense? I think so far it's pretty simple. Hopefully it's simple for you as well. Okay, so let's move on. The next topic is homogeneous linear ODEs with constant coefficient. By the way, let me see. By the way, I think your homework asks you to compute 3x3 matrix. 4x4 matrix? Oh my god. That's kind of mean, to be honest. Yeah, I can't help you. Yeah, there's a 4x4 matrix, isn't it? Oh, never mind. Find the general. 3x3. Let me see. Yeah, it's 3x3, so it's not too bad, I would say. Because last semester, students were asking to compute 4x4 matrix, like determine a 4x4 matrix was a pain. But yeah, this is better, slightly better than 4x4. Anyway, back to this. Homogeneous linear nth order ODE with constant coefficient. Make sure we have constant coefficient now. So we're talking about homogeneous linear, those two didn't change, and then it's constant coefficient. So those are all constant. They are not functions of x anymore, they are constant. Anyway, given this, we can try the solution, which is y equals to e to the mt. And using that, you can get the characteristic equation. This is really, really important. How do you find the characteristic equation of ODE? It's really important. So if you observe those two equations, you'll see that we keep the coefficient, and then m times the power is the same as the order of the derivative. Okay? So the degree of the derivative is n here, then it's to the power of n. If it's n minus 1 here, then it's to the power of n minus 1, and so on. And when you got the characteristic equation, and you try to solve this, you have three different cases. The first case is distinct real roots. The second case is repeated roots, and the third case is complex root. For distinct real solutions, it's pretty simple. So if they are all distinct, then your solution is just C1 e to the your solution t plus C2 e to your solution t, and so on, where your c's are all arbitrary constant. So here is an example. Since we're running out of time, we'll do this together. So first you keep your coefficient, so 2m to the power of, this is second derivative, so it's to the power of 2, minus 3, y prime is the first derivative, so it's m to the power of 1, so m itself, minus 2, y itself is like, it's like to the power of 0, so m to the power of 0, which is 1. So this is a characteristic equation of our ODE. Now we just need to solve this. So when you solve this, you'll get m1 equals to -1/2, and m2 equals to 2. So your general solution is just gonna be y equals to c1 e to the negative 1 over 2x plus c2 e to the 2x. And now you see that you're given initial value. That means you can compute those back in to find your c1 and c2. You're given y prime, so you need to find your y prime. Y prime equals to negative 1 over 2 c1 e to the negative 1 over 2x plus 2 c2 e to the 2x. Now plug your initial value back. Y0 equals to c1 plus c2 equals to 0, which means c1 equals to negative c2. Y prime 0 equals to negative 1 over 2 c1 plus 2 c2 equals to negative 1. So you can get negative 1 over 2 c1 minus 2 c1 equals to negative 1. So negative 5 over 2 c1 equals to negative 1. That means your c1 equals to 2 over 5 and c2 equals to negative 2 over 5. So eventually your solution becomes 2 over 5 e to the negative 1 over 2x minus 2 over 5 e to the 2x. That's for distinct real roots. Okay? Now, if you have repeated roots, any question for this example? Nope. Okay, cool. So if you have repeated roots, it's really similar to before, except for each of the repeated roots, you multiply your solution by t or x, whatever your independent variable is. So for example, your y1 and y2, no, your m0 and m0, they're all m0. So for the second one, you multiply by t, so y3 will be c3, y3 equals to c3 t squared e to the m0t, because we multiply by t on this one, and c4 will be tq and so on. Okay, so it depends on how many repeated roots you have. For each one you have, you multiply by t. So for this one, let's convert it. Let's find its characteristic equation first. So m to the power of 4 plus 3m cubed equals to 0. m cube, no, m cube, sorry, m cube m plus 3 equals to 0. So m equals to 0 with multiplicity of 3, because it's to the power of 3. So it equals to 0 3 times. And then m equals to negative 3. In this case, your y1 is going to be e to the 0t. y2 is y2 and y1, they have repeated roots, so multiply by t. So that's going to be t times e to the 0t. And y3 is going to be t squared e to the 0t. And y4 is going to be e to the negative 3t. So in this case, the general solution is going to be y equals to c1 plus c2t plus c3t squared plus c4 e to the negative 3t. Any question? No? Yes? No? No? Okay, cool. The last one is complex root. So if alpha plus beta I and alpha minus beta I are the two complex solutions of the characteristic equation, then the solution you can write it as this. But this is not convenient for us, so we use Euler's formula to write the solution in this way. So this is the one we actually use. They want you to write it in this way. Okay? So e to the alpha t times a and b are constants, a cosine beta t plus b cosine beta t. And let's try this example, and that's the end of the tutorial. Again, let's write the characteristic equation first. M cubed minus 4m squared plus 5m equals to 0. So m times m squared minus 4m plus 5 equals to 0. That means your m equals to 0 or m equals to 4 plus or minus square root of 16 minus 20 over 2. That's going to be 2 plus or minus I. When we reach here, you should find what is your alpha and what is your beta. So if you look at this, your 2 is your alpha, and the coefficient of I, which is going to be 1, is going to be your beta. Okay? So your solution is going to be y1 equals to e to the 0t. y2 is... Actually, let me just write the general solution directly. Saves us time and space. Y equals to C1. E to the 0t is 1. So C1 plus C2. C2 is your constant, so that's going to be A here. And then e to the alpha t. Alpha is 2, so e to the 2t. And then cosine beta t, beta is 1, so cosine t. Plus C3 e to the alpha t, so e to the 2t, sine to the beta t, so sine t. And that is the final solution. Okay, I think that's it. Hopefully that's going to be helpful for your assignment. I think I did easier version of your assignments because your assignments are all higher order. But it's similar idea except you have more computation. So hopefully you can do your assignment now. Anyway, if no question, that is the end of the tutorial. Anyone has any question? Okay, cool. Good luck on your test if you have one, and have a good reading week.